Welcome to this short tutorial about the Stiebel Eltron heat pump tool. The tool will guide you through the design process for a hydronic heat pump tool. It will also create calculations, reports for energy savings, CO2 savings, and it will tell you how much your heat pump will consume electrical wise. So it will give you all these informations. You can find the tool on different websites. Here, for example, I am at Stiebel Eltron UK, but you also have different climate data that you can choose from. So here I prepared an example for Australia. It always works the same. So from top to bottom here, the questions about your application, your use case, and results here from top left to right. You have the results. Let's actually switch to the Australian version. So I just can click here that everything is correct. You have seen there are different options and variations for the tool by itself. So now we are in the version for Australia. Good. As I said, questions left top to bottom, and then results from left to right up here. First questions are about the build. What kind of build is it? Couple of questions. Single family home, yes or no? Is it multi-family house? Commercial application. Then installation standard. It wants to know how good the quality of the build is. By choosing an old building, the tool changes this temperature threshold here. So in this case, old building, the heating system will start working at 15 degrees. You can imagine if this would be a very well insulated house, the heating system can wait longer, so can get colder and you don't have to heat because your house is well insulated. So if you choose passive house, for example, it goes down to 10 degrees. So the heating system will just start to work at 10 degrees. But for our example here, it's a renovation job. It's an older building. Maybe they changed some stuff, changed the glazing or added a little bit of insulation. The heating starting point at 15 degrees is okay. So we keep it like it is. Then it wants to know how many people are in the build. That's relevant for the domestic hot water production afterwards. Heat load, this is interesting. You need to know the heat load. You have to calculate it somehow. In some countries, they use the historical energy consumption from the last 5 years and then calculate it back to a heat load. That's one possibility. I calculate the builds with my spreadsheet. So I use my Excel spreadsheet and I calculate the losses through transmission, so through walls, roof, glazing, and also ventilation losses. That together equals the heat loads. So you can do that as well. But you need to know the heat load. That's really crucial. So in our case, we need, for example, 12 kilowatts. Just type in 12 kilowatts, done. Where is the build? It's in Australia, and we take the classic example and put our build to Melbourne. Okay, you can click on the map directly, which actually is a little bit harder, or you can just jump into the list and then it chooses the climate data. Melbourne 2 degrees is now chosen. Switch off times, wouldn't say that it's relevant for Australia. So if your energy supplier switches off electricity certain times, then you can choose switch off times here. So in Europe, it's quite often that the energy supplier, when they have peak consumption, they switch off some appliances. but I would say for Melbourne, we just keep it on 0, no switch off times. Okay, what you now see is here on this screen, you have your line here that indicates the heat load. So we start at 15 degrees and then the heat load goes up to 2 degrees, which is our design temperature, the coldest temperature. And at 2 degrees, um, the heat load is 12 kilowatt. Okay, so that indicates the heat load of the build. The lower red line is the minimum heating capacity of the heat pump that we have chosen, and the upper one is the maximum capacity. Everything which is a little bit red between here is what the machine can actually do inverter controlled. Okay, let's go further. So actually we see that our capacity is a little bit outside of what the machine actually can do. So let's go further. We want to install an air-sourced hydronic heat pump outside. Okay, that's already good. We can also choose indoor installed heat pump. So that's also something that we have in the portfolio. Okay, now I've said that the heat pump is slightly on the smaller side. We can just make it a little bit bigger. Let's go to WPL 20A. Okay, still a little bit outside. Let's use the famous WPL 25, and now we see it's right in the area where the heat pump can adjust the capacity. So that's okay. We can leave it like it is. We just need one heat pump. Flow temperature, also very crucial for efficiency. You need to know the minimum flow temperature. Is it the underfloor heating system or is it the radiator system? So in our case here, I use a 50-degree radiator system. If it's more than 50 degrees, it will hardly be possible to touch the radiator. So that's a rule of thumb. But 50 degrees is already quite high for winter. So I keep it on 50. The tool could also go higher if you want to. The limitation of this machine, of this heat pump, is 65 degrees. But just keep it on 50. We don't need a second heat source, so the machine can do it just by itself. We have no special heat pump rate, we just have household electrical tariff. This one is also interesting, outside temperature driven. So this heat pump will run weather compensated. So there is a sensor outside hanging on the wall somewhere and measuring outside temperature and uses that information to adjust the flow temperature. So when it's cold, flow temperature is high. If it's just on the edge somewhere to heat or not to heat, then the heat pump will go lower with flow temperatures. So just use outside temperature driven. For some special applications, you can also choose fixed value control. Then the heat pump just runs on a thermostat, if you want to call it like this, just fixed temperature. For best efficiency, outside temperature driven is the best. So just use this one. Okay, that's all done here. This heat pump can do quite high flow temperature, so it's also possible to do domestic hot water. So I can choose with heating heat pump. I need to know how much domestic hot water we use in this household. So it asks the question here as well. Ask the customer, special showers, big bathtubs, stuff like this are indicators for high consumption. Here in my case, I just choose normal consumption, just 25 liters, 60 degrees though, so that's a little bit of energy as well, but just normal. And remember, I told the tool we are 4 people, so it uses these 4 people times 25 liters. Here in our case, I just want to have 60 degree in the tank because also of Legionella and stuff, so I just have chosen 60 degrees. Do I have a water circulation? No, I don't have one, but still I have a little bit of losses. 5% as default. You can go higher if you really have old installations and a lot of losses, no insulation, you can make that higher. Yes, the tool uses 340 days of usage, so there's a little bit of holidays deducted here already. And now we are done. So for our system for heating and domestic hot water, that's all that we need to know. Now we can go through the results. Heat demand is what we have to put into the house. So that's the blue stuff is domestic hot water and the red stuff is heating. If this would be a new house, well insulated house, the part of room heating will be quite small. Passive house goes up to 50-50 uh, parts for domestic hot water and for heating. So here you see it's old house, it's not well insulated, so a lot of energy goes into heating and just a little bit into domestic hot water. So the actual input into this house is 23,000 kilowatt hours. The electrical demand is around about 5,700 kilowatt hours for heating and domestic hot water. And as I said, the part for heating is quite high. Costs, you can use a electrical tariff in the background and then it uses that to calculate. So here I think I have 20 cents or 25 cents per kilowatt hour. So in my case, you see the costs here, $1,400, $1,500 a year. Performance, I think this one is interesting. You see the COPs, the coefficient of performance. So for heating and domestic hot water, in our case, not a great house, to be honest, 12 kilowatts, 4 people, domestic hot water, average COP is 3.9. In heating, it's 4.1, and for domestic water is 2.8. This machine will run on average inverter speed of 56%. So it will not reach 100% capacity. It will run on minimum speed and then ramp up slightly a little bit. But average is just 56%. Can do also comparisons in energy costs to fossil systems, and you can also calculate savings in CO2. If you have your own solar system, PV system, you can make a reduction here as well. So PV systems should be CO2 free in electrical production, more or less. So if you can run your heat pump on your own electricity, it's quite a game changer, I would say. Climate indicates climate data. Documents will show you documents on the heat pump, and project will give you the opportunity to fill in some customer data, your own data, and then you can create a PDF. Here you can put in some information from your customer. Heat load 12 kilowatts at +2 degrees C. Okay. Put in some notes and then press print project, and then it will create a multiple page PDF for your customer. What I want to do now is do a quick comparison to a geothermal system. So performance is what we want to compare when we are doing the comparison with geothermal. We have a seasonal COP of 3.9, heating 4.07, and domestic hot water 2.76, and an electrical consumption of 5,736. Let's play a little game and use a geothermal heat pump. Let's just go back here to the initial screen, and now we can just change the heat pump. We go to brine. Brine water heat pump indicates a geothermal heat pump. First thing that we see, the smallest heat pump is not big enough. So we go a little bit higher, go to a WPE 08, still a little bit small. Let's go one number bigger. 12 is enough, I would say. But there's a big question mark. The efficiency and the power capacity of these geothermal machines has a big relation to the source temperature. So European climate is a little bit colder, Northern European climate. So my geothermal probe that I have in my house gives me 6 to 8 degrees during the year. So you need to calculate that. You need to know how much is the temperature coming from your geothermal source. I would say from my little experience in Australia, it should be possible to have 8 to 10 degrees in your geothermal probe. So let's be a little bit pessimistic and use 8 degrees as a source. And now we have seen that the capacity of the machine went up even a little bit higher. So now we think we use 8 degrees as source temperature, average source temperature during a year. What happens now to efficiency? That's going to be the most interesting part. Heat demand is still the same. Electrical demand is now a lot smaller. So we had before 5,736. Now we have just 4,695. So how much is the savings? That's 4,695. More than 1,000 kilowatt hours is saved just by using a geothermal heat pump. Costs, of course, there's a reduction there as well, but I want to know efficiency. That's what's interesting for me. So from the air sourced solution before, we saw that the average COP was 3.9. Now we have a 4.8. So in heating, this solution has a 5.3, and before that we had a 4.1. So that's a lot better. Same here, must be more or less the same percentage in difference, 4.77, 3.9. Yes, it's 22 to 30% savings for geothermal heat pump. So I would say if you have really a good temperature source, if it's, let's be optimistic now and make it 10 degrees, now we have a seasonal COP of 5. So I think that's realistic here. In my house, I just do heating, just for comparison, Swiss climate, very cold climate, a lot colder than Melbourne. Um, I have a COP of 6.5. Geothermal probe, 100 meters, 6 kilowatt load, 6 kilowatt heat pump, on the floor heating, and COP is 6.5. So I think that's pretty realistic. So this is how you can use the tool. You can make your variations, you can do your own cases, go through them, undersize the heat pump, oversize the heat pump, look what's happening. I think that's the interesting part of it. And in the end, you can print it out, give it to your customer, and help him with his decision. So here you see now it works. I wish you a lot of fun with playing around with the tool. If you have questions, don't hesitate to write us an email, give us a call, send us your reports. We will help you through the first designs for your heat pump systems. I hope this was helpful for you, and I'm looking forward to hear more from you, and I hope you can join further trainings about our toolbox. Thank you very much, and goodbye.